Hello everyone, we are going to start section 4.5 and here we are going to talk about coordinates and bases. We're going to start with definition. If V is any vector space and set S, which consists out of vectors v1, v2, vn, is a finite set of vectors in that space, then this set is called basis for V if number 1, S is linearly independent. Number 2, S spans whole space V. Couple of examples. Example number 1. For example, let's consider two-dimensional space and the set of two vectors I and j. Two-dimensional space and R2. So, we do know already that they are linearly independent, right? I'm going to formally check it, but k1 vector 1, 0 plus k2 vector 0, 1 equals 0. We do know that the only solution is k1, k2, if I add these two vectors equals 0. So the only solution here is k1 equals 0 and k2 equals 0. Trivial solution, linearly independent. Well, we already kind of proved it once, but just to check these 2 points. Does it span space R2? Well, we know that any vector in R2 can be expressed through coordinates v1 and v2, right? So if I use v1 and multiply it by vector I, and I use v2 and multiply it by vector j, these are going to be linear combination of vectors I and j with coefficients v1 and v2, which is going to describe any vector v. Bases like this, which consist out of zeros and ones, are called standard bases. So this one is standard. Okay, can other vectors be bases, form bases? Example number 2, v1 equals 1, 2, v2 equals 3, 3. Is this set going to make a basis? Is it a basis for R2, the same space? Well, let's check if they are linearly independent. A little bit long, but we can do it, right? So, k1, 1, 2 plus k2. I'm doing linear combination, and I'm planning to set it to 0, 0 to just kind of check. So I have k1 plus 3k2, the first component, and 2k1 plus 3k2, second component, equals 0, 0, which is going to produce two equations. k1 plus 3k2 equals 0, and 2k1 plus 3k2 equals 0. If I subtract first equation from the second one, I'm going to get minus k1 equals 0. So my first solution, if I plug it into the first equation, I'm going to get k2 equals 0. So we have only trivial solutions, so linearly independent. Now we have to check the second condition. Second condition, span. Well, guys, to make it span, I'm going to actually use the very same system I already used. I'm just going to modify it a little bit. To make it a span, we'll need to make sure that any two-dimensional vector can be expressed through the linear combination of these two, right? So instead of 0, 0, I'm going to put some two-dimensional vector, which is going to be having coordinates v1, v2. So v, that's going to be my arbitrary vector. Okay, So, well, solution is going to mostly stay same, except I'm going to have v1 here and v2 here. If I do the same operation, instead of like minus k equals 0, I'm going to get minus k1 equals v1 minus v2. And then I can plug it in here back and get k2. So v2 minus v1 plus 3k2 equals v1, from where 3k2 equals v2 v1. I think I'm moving v1 over here, minus v2, so k2, sorry, k2 equals 2v1 minus v2 over 3. And this k2 and this k1, if you multiply it by -1, it's going to produce k1, are going to work as coefficients, which are going to create a linear combination for any vector v. So check the second one. So it's going to be a basis. This basis is not standard basis, but it's still a basis. Okay, so now let's talk about kind of interesting stuff about basis. We're going to consider more different bases for different spaces in class. But right now, let's talk about some theory. The theorem. Uniqueness of basis representation. Why do we need these conditions on basis to be linearly independent and to span? Well, to span is okay, we understand that. If we can use several vectors to represent any vector as like linear combination, well, kind of achieves our goal by using coefficients as coordinates. But like, why do we need it linearly independent? Let's see. So, if we have a set S consisting out of vectors v1, vn, and this set is a basis in V, then for any V belonging that V can be represented in the form V equals C1 V1 Cn Vn linear combination in exactly one way. Well, theorem is telling us that if we find a linear combination which represents vectors in our space, the coefficients of this linear combination are going to be just unique coefficients. So you're not going to have another set of coefficients which is going to represent the same vector. How I'm going to prove the theorem? I'm going to assume that we do have another set of representation. So I'm going to write down that suppose there are two ways. And I'm going to write down. So first, v1 equals c1 v1 and other vectors cn vn. And v also equals, I don't know, c1 with tilde v1, cn with tilde vn. Now, what are we going to do? I'm going to subtract this like two vectors, and I'm going to get 0 on this side, right? And on this side, I'm going to combine the coefficients in front of the same vector. For example, in front of v1, there are two like coefficients, and all others. And cn minus cn tilde in front of vn. By the way, I put n in the wrong place here. Well, what do we know about vn and v1? Since v1, vn linearly independent, linear combination equals to 0 linear combination has only trivial solution. Trivial solution means that this coefficient must be equal to 0, this coefficient must be equal to 0, and all of them. But if C1 minus C1 tilde equals to 0, means that C1 equals C1 tilde. And for all of them, Cn equals Cn tilde. So basically, if you have two different representations, they are the same representation. So why do we need this? We'll need to make sure that if we have a set of coordinates, that's a unique set of coordinates. We don't have another set of coordinates, which is totally different from what we have. So the idea is kind of to make sure that we have only one set of coordinates, since we are planning to use it for something probably. So we proved the theorem, right? So now, guys, we can set up definition. Definition. If you can represent vector v through the linear combination of some set, then for S, I'm going to write down v1, vn basis. Then the coefficients c1, c2, cn are going to be called coordinates of vector v relative to basis S. Usually we're going to write it down like this, vector v, then we'll take in parentheses, write down S, showing that these are the coordinates in this basis, and if you choose another basis, coordinates can change. Okay, maybe I should consider one example. Of like doing the coordinates. So give me a second. Example, let's make example in red. Example. Consider our set of two vectors, v1, which is 1, 2, and v2, which is like 3, 3. We already proved that this is basis from the previous example, right? Now, let's consider vector u, arbitrary vector in 2 dimensions, with coordinates 5, 7. And these 5, 7 are just regular Cartesian coordinates. I'm going to put normal coordinates. Now, the question is, what are going to be the coordinates of this vector u in basis S? The question. Well, I did pick up the points to make it a very, very easy example. Let's look. I'm going to just take two vectors v1 and add vector v2. I'm going to just verify that it's going to work. So 2 of 1, 2 plus 3, 3 is going to be what? 2 by 1 is 2 plus 3 is going to be 5, and 2 by 2 is 4 plus 3 is going to be 7. So, well, basically I picked up vector u to make it very easy to represent, so to not solve any equations here. So we see that vector u can be represented as a linear combination, and the coefficients of these linear combinations are 2 and kind of 1, which we don't have over here, but we can do it. So now we can write down that the representation of u in the basis of this like set of two vectors is going to be 2 and 1. And this is going to show you which basis you used. Okay? I think that's it. In class, we are going to consider more examples of different vector spaces and bases.